Hi, also we're looking at 3.8. This is calculating energy transfer when we have phase change and temperature change. So we're just shoving together everything we've learned about calculating energy transfer into one problem. And I picked number 4 from your packet worksheet because this one is kind of tricky. So I wanted to show you a tricky one on the tutorial. So let's take a look at the problem. The first thing we always need to do is we need to draw the heating or cooling curve, the temperature time graph. If you do not draw the temperature time graph, you are not going to get the right math. We need the graph. So it tells us 65 kilojoules. I'm just going to go ahead and convert that to joules. So 65,000 joules are added to 150 grams of ice at 0 degrees Celsius. So, okay, I start at 0 degrees Celsius. I know that. What is the final temperature of the water? So it's telling me that ice is going to melt. So that's the first part of my graph. And then it's going to warm up. So that's the second part of my graph. I have a phase change because it's ice. And in order for that ice to turn into water, it needs to melt. And then I have a temperature change. So that means I have 2 regions in this graph. I'm going to call them Q1 and Q2. And we know that we need different equations for a phase change versus a temperature change. So for Q1, that's a phase change. So I'm going to use Q equals mH. Since it's melting, I'm specifically going to use heat of fusion, or H sub F. I would use heat of vaporization if it was boiling. It's melting though, so I'm going to use heat of fusion, H sub F. Remember, those values are at the top of your worksheet. They're always given to you. They are constants. I can't use Q equals MC delta T here because there is no delta T. Q would be 0, but I know Q isn't 0. So I have to use Q equals mH here. Now for Q2, there's a temperature change. So for Q2, I'm going to use MC delta T. Now remember, this is water as a liquid water, so we would use the 4.18, again, at the top of your worksheet for our C. Even though it starts as ice, it's not ice by the time it starts heating up. It is water. So we use liquid water C. The last thing I need to remember is this idea of Q total, because 65,000 joules is Q total. It's the whole thing, all the energy that's put into the system. So remember, Q total equals Q1 plus Q2. Okay, so we have everything we need now. Now here comes the algebra. We need to do some substitution, but it's very simple substitution. We're just plug in equations in for Q. So Q total, I know, is 65,000 joules. So I'm going to set that equal to my Q1 plus my Q2. So that means I need these equations. So my equation for Q1 is mH sub F, so M, mass, from my question is 150 grams, put this in parentheses, times heat of fusion for water, again at the top of your page, 334 joules for every gram. And we know that's positive because it's melting. So again, this set of parentheses here is Q1, just so we can keep track of that. Plus, your Q2 is going to be M, 150 grams again, times C, where we talked about this. This is liquid water because the ice has melted. So 4.18 times delta T. So T final, that's what we're solving for, minus T initial from our graph here, 0 degrees Celsius. So after that ice melts, it's still at 0 degrees Celsius until it heats up. So that's the equation. Honestly, that is the hardest part, is just to get the correct graph and get the correct equation. From here, it's just algebra, right? So we need to do 150 grams times 334. We are also going to do our sig figs within each set of these parentheses here, because it's kind of like we're doing 2 separate equations. We just combine them together into one, but technically they really are 2 separate math operations. So when I do 150 times 334, I'm going to go ahead and round that to 50,000 joules. Now I know that's 1 sig fig, and this is 2 sig figs. I could write it in scientific notation, but I don't want to. So I'm just going to leave it as 50,000 because whether it's 1 sig fig or 2 sig fig, it's not going to matter when I add it together if the number would be the same. Like it would be 50,000 joules if it was 2 sig figs. It would be 50,000 joules if it was 1 sig fig. It doesn't actually change the number. So it's fine to write it this way for now. Plus, when I do my 150 times my 4.18, I round it to 2 sig figs. I'm going to end up getting 630 times TF minus 0. You guys know anything minus 0? It's just TF. So I can get rid of that 0 because it's 0. It doesn't mean anything, right? It's a 0 temperature. If I subtract 0 from anything, it's not going to change the number. So that applies to variables too. If I subtract 0 from whatever TF is, it's still going to be TF. It's not going to change the value. So I could just change that to 630 times TF. Of course, equals 65,000 joules. And again, from here, all we're just doing some algebra, right? So I'm going to subtract out my 50,000 from both sides. And that gives me 15,000 joules equals 630 times TF. Those are being multiplied. So I'm going to divide both sides by 630. By the way, I didn't show these units canceling. Those grams cancel. Those degrees C cancel. So this is 630 joules. Just so we're clear on that. These grams cancel here too. So joules, joules, joules. Okay. So 15,000 divided by 630. Do that math. That's going to give us a final temperature of 24 degrees Celsius. 2 sig figs. So again, the hardest part of this is just getting this right equation here. Step 1, you have to draw the temperature time graph. If you do not draw the temperature time graph, you will not get the right equation. You have to draw the temperature time graph. Then write out your equations for each region. Write out your equation for Q total, and then we plug in from there and do the algebra. So these are long problems. Just take them slow. Take them slow, take them chunk by chunk, and it's not as scary as it looks.